Hi, welcome to the Vectors Summary. You've actually completed the Vectors topic now, so we're just going to have a quick run through of what you should have learned from this topic. Okay, so the first thing we looked at was magnitude, and we said that was just another word for size or length. What a vector actually was, so it's just something which has both a magnitude and direction. And we looked at representing vectors, and we said that can be done with directed line segment diagrams. So there's an example with letter symbols using capital letters or lowercase. So this vector could be called lowercase u underlined, or the vector AB with the arrow above it. Or it can be represented by column vectors. And for this diagram, it would be the column vector 4, 1. So just to remind you, a column vector just describes the journey from the start of a vector to the end of the vector. We can have these in two-dimensional, which means it would have an x component and a y component, and a three-dimensional column vector, so it would have an x, y and a z component, and they are just written like coordinates but vertically. Now, using these components, we can then calculate the magnitude or the size or length of the vector, and it's just using Pythagoras' theorem. So that's your version for 2 dimensions, and that's your version for 3 dimensions. We looked at equal vectors, and basically we have equal vectors if the vectors are the same length and going in the same direction. So here we've got a vector u. We can see that goes along to the right 5 and up 2. We've got a vector v, which also goes along to the right 5 and up 2, so therefore vector u equals vector v. We looked at negative vectors as well, and basically we just have a negative vector when the direction of one vector is reversed. So here if we take the same example, vector A this time it's been called, and it's 5, 2 again. But if we reverse the direction of the arrow to get from the beginning to the end, we need to go 5 to the left this time and 2 down. So we represent that by negative 5, negative 2. So you can see we've just swapped the signs of the symbol and swapped the signs of the components values as well. We said that vectors can be multiplied, and it's just like multiplying any other number. So if I have a vector here, which would be the vector 3, 1, and that's vector u, if I wanted to get the vector 2u, I would just double the length of the vector if I'm drawing it. So that would be 6 along and 2 up. Again, as a column vector, I would just write it as 6, 2. Now, because we can multiply vectors, we can also then find parallel vectors, because if A is a multiple of B, so if one vector is a multiple of the other, then both the vectors are parallel. So for example, here I have a vector which goes 9 to the right and 3 down, so 9 minus 3 for vector A. This second vector B is only 3 to the right and 1 down, but we can see that vector B is a third of vector A, so because one is a multiple of the other, then B is parallel to vector A. We also spoke about resultant vectors. We just said that's the vector you get by adding or subtracting sets of vectors. The shortest distance from the starting point to the finish, from point A to point B, is also called the displacement. And we can show a displacement by adding vectors together. So if we wanted to draw a diagram to represent that, this vector here, u, is the vector 3, 1. We've got a vector v, which is 2, negative 3. If we want to add those two vectors together, we draw the vector u, so 3 to the right, 1 up. And then at the end of vector u, we attach vector v, so 2 to the right, 3 down. Once I've drawn that, I just join the two ends up, and that gives me my vector u plus v. I can also represent this as a calculation. So using the column vectors, it's 3, 1 plus 2 minus 3, and that would give me 5 minus 2. And if I trace the path from the start to the end, and see I need to go 5 to the right and 2 down, which confirms my calculation. Likewise, we can also subtract vectors, so in a similar manner, if I have a vector u again, which is 3, 1, and v, which is 2 minus 3, this time if I want to do u minus v, so I draw the vector u, so my 3 to the right, 1 up, and from the end of that vector I draw the reverse of vector v. So instead of it being 2 to the right and 3 down, it would be 2 to the left and 3 up. So the negative of vector v. And then join the beginning to the end, and that would give me u minus v. We can do it as a calculation again. So 3, 1 subtract 2, negative 3 this time. So 3 subtract 2 is 1, and 1 subtract negative 3 is 4 because we have the double negative there. So again, if we go from the start to the finish, we can see if we go 1 to the right and 4 up, that will get us to the end point of the vector and confirming our calculation. We also spoke about position vectors, and we said that that was just describing the journey from the origin to a specific coordinate point. It can be in 2 dimensions or 3 dimensions again. So if we have a coordinate point A in 2 dimensions, which is xy, then the corresponding column vector A underlined would be xy written vertically. If we have a coordinate point B which is in 3 dimensions, then the corresponding column vector B underlined would be xyz written vertically. If we know position vectors, then we can also work out the vector between 2 coordinate points. So for 2 coordinates A and B, the journey from A to B can be found by doing the column vector of B subtract the column vector of A. So it's always the column vector of the second letter subtract the column vector of the first letter. So here we've got a coordinate point A which is 3, 5, so the column vector lowercase a underlined would be 3, 5, and B is minus 1, 8, so similarly the lowercase b underlined is negative 1, 8. If we want to find the vector going from A to B, then it would be minus 1, 8 subtract 3, 5, so we would have negative 4, 3. Another thing we looked at was vector journeys, and we just said that that was a description of a vector's displacement. When we're doing vector journeys, we need to remember to write the path in the capital letter symbols first, then change to the lowercase letters. And remember, we can only go along a path that's labelled with lowercase vectors, and that there may be more than one possible path. So here we've got a parallelogram PQRS. X is the midpoint of QS, and we're being asked to find certain vectors. Remember to always fill in any information that you know on your diagram first. So here we can fill in vector A and vector B on the sides RS and QR respectively. This will help us because it will give us more routes to take. So here we've got PR, so one possible route to get from P to R is to go along PQ and then along QR. So that gives us the vector journey A add B. Second example is QS. So to get from Q to S, one possible route is to go from Q to P and then P to S. So that gives us the vector journey negative A add B. Next one is QX. So to get from Q to X, if we think about that as being halfway along the vector QS, we've already worked out that QS is negative A add B, so we just need to half that, and we get negative half A plus a half B. The last example is PX. So to get from P to X, we could go along P to Q and then QX. So we know that P to Q is vector A. QX we've just worked out in part C. So it's A subtract a half A plus a half B. So we end up with a resultant vector of a half A plus a half B. We're almost at the end now. So now we're looking at 3D coordinates. And what we need to remember is this time we have an X, a Y and a Z axis. And the X axis moves left to right, the Y axis moves forward and back, and the Z axis moves up and down. For 3D coordinates, remember, we always do them alphabetically, so you always do X first, then Y, then Z. So the two examples here, we can see for coordinate r, we start at the origin, go 1 to the right, 3 forward and 5 up. So that gives us the coordinate 1, 3, 5, or the column vector 1, 3, 5. For part B, we have the coordinate point S. So this time you can see from the origin we're going 4 to the left, so that's -4. 4 back, so that's also negative, so sorry, not 4 back, 2 back. So that's also -2, and then 1 up. So we end up with a coordinate S as -4, -2, 1, or column vector -4, -2, 1. The last thing we looked at was unit vectors, and we just said that that was a vector that had a length equal to 1 unit in the x, y, or z direction. So we call the unit vector in the x direction I, and it has a column vector of 1, 0, 0. J is the unit vector in the y direction, and it has the column vector 0, 1, 0. And k is the unit vector in the z direction, and it has a column vector of 0, 0, 1. Any column vector can be expressed in terms of unit vectors, and vice versa. So for instance, we have 2i plus 3j minus 4k. That can be written as a column vector 2, 3, minus 4. We have I subtract 2k, so that can be written as 1, 0, minus 2. Remember, I corresponds to the x direction, so that's why we have an x component of 1. J corresponds to the y direction, and there's no j term, so therefore the y component is 0. And then we have minus 2k, so the z component is minus 2. Likewise, if we look at the third example, we just have -3j. There's no I term, so therefore there's no x component. There's no k term, so therefore there's no z component. There's just a j term, which corresponds to the y component, so therefore the column vector is 0, -3, 0. And that finishes our recap of the vectors topic. Now we're going to get you to have a go at some questions.